Good afternoon to all of you. So today, in the last class, we learnt about about registers. Today, we are going to learn about synchronous counters. Okay. So the name synchronous means all the flip-flops are going to be clocked by the same source, like we are going to use the same clock for all the flip-flops. Now let's take an example and try to understand how this works. So first we will talk about try to implement a 3-bit binary counter. So if I have to implement a 3-bit binary counter, I will require 3 flip-flops. Okay, so 3 flip-flops are connected in series out here, right? 3 flip-flops are connected here. All are being given the same clock. Okay, that is important because this is synchronous counter. After this class, we will see asynchronous counters are also there. So I am stressing this word synchronous counter because I am going to give the same clock here. So it is a 3-bit binary counter. So initially 0, 1, 2, 3, 4, 5, 6, 7, and then it has to come to 0, right? So how to design these counters, right? So all these counters, if I see here, so seeing this table itself, I can get a fairly good idea how to go about designing this counter. If you see here, with each clock, this is changing from 0 to 1. The next clock, this is changing from 1 to 0. Again, next clock, this is changing from 1 to 0, 0 to 1, 0 to 1 to 0, 0 to 1, 1 to 0. So it just come this state again. So if you see here, if I use a T flip-flop, right? T flip-flop is, what does a T flip-flop do? It will toggle with every clock. Right? Once in each clock, the output will state from 0 to 1 and 1 to 0. So I can use an T flip-flop here to implement this bit. What about this bit? If you see here, so if you see this here, right, when is it toggling? When this is 1, right? Initially this is 0 here, so it is not toggling. When this is 1, this is changing from 0 to 1 here, right? And then this has become 0, so it is continuing the state as 1 here. So if I use a T flip-flop, and if I take that T input for this stage from the previous state Q, then this will also can be implemented. Okay, let me repeat it. This is an T flip-flop straight away because every clock it is changing. Okay, here also I am giving the same clock, but it is not changing with every clock. Here it is, right? It is from here to here. When it is moving, it is not. So what is the previous here? If it is 0, it is not changing. If it is 1, it is changing from 0 to 1 here. Now this has become 0, so it is continuing to remain 1 out here, right? So it is not changing. Similarly, if this is 1, it is toggling. So I can take an for this flip-flop, I can take an T input, right, and from the previous Q. This Q becomes T for this. Similarly, here also, if you see here, it is all 0, 0, 0, 0 here. When this is 1, it is not making a toggle. Okay, right. It is making a 0 to toggle when both of them are 1 here, right? When both of them are 1 here, it is making a toggle here. Then again 0, 0, it is continuing to remain the same state. 0, 1, it is continuing to remain here. 1, 1, 1, 0, it is 1, 1, 1, right? And then the next state. So whenever there is 2 1s here, this is making an transition here. Whenever there is a 2 1 here, so that means this toggle should be based on two and of these two, right? So this is what is explained out here, whatever we discussed now. So I can use an T flip-flop, right? So how to make an T flip-flop? I can join J and K, right, together. For if I have to use an JK flip-flop, if I short J and K, so then it will become 0, right? If I give 0 here, then J is equal to 0, K is equal to 0, it will remain in the previous state. And if I short this and if I give 1, then J equal to 1, K equal to 1, the state has to toggle. So so the T flip-flop can be realized by shorting J and K and using that as an T input, right? Is it clear till here, Sachin? Yeah, Abhishek, is it okay? Shall we move it? Okay. Now if you see here 4-bit synchronous counter, now how to make the 4-bit synchronous counter. Here we discussed about an 3-bit, right? Here I am talking about an 4-bit, so it will start from 0 and it will reach till 15. So if you see here, the clock is given, the same clock is given to all of them, right? And then this count enable signal, that means whenever I am giving the count signal, okay, go ahead, start counting. So this is the count enable signal. For the least significant bit, I am giving j and k equal to 1. So it will act like an T flip-flop. The next one, I am taking this signal and I am taking Q and putting an AND, right? So and then I am giving it to JK out here, right? So this is what we read, right? First one is going to be a toggle. Now the second one, okay, I have to give only when this is an 1 out here, right? Only then it has to make a transition, right? So also I am putting this a clock enable signal also here. That's sorry. Here, okay, if this is 0, so nothing would move. So this is just to enable all the circuits. So I am taking this Q and giving it here, right? For the next stage, here I am putting one more AND gate. Obviously I have to AND A0 and A1. So already I have taken this one AND here, so I am taking one more AND here, right? So now this will become this output will be, right, J only when both of them are 1, only then this J will be 1, right? J and K will be 1 here. And for the next state, again you take a Q and you put one more AND gate. So this is how an 4-bit synchronous counter would work. Okay, is it clear to all of you? I can repeat it in case you have any doubts in this, right? So how did we come to this circuit? It is just by seeing the state, right? It is 0. This is toggling with every state. Okay, 0 every clock it has to toggle. So I have put directly count enable signal there, right? Directly. So whenever the count signal is high, this will count. If I go back here for the next state, okay, this has to toggle only when this is 1 here. So I have put an AND gate and taken an 1 here, right? And now the next one, if I go to the table here, if it is only when it is 1 1, it is making a change. 1 1, it is making a change. So that is why I have put one more AND gate. So here one AND operation is already taken care of. I have put one more AND and taken a Q from here, from this state. So this will, and now with each clock it will start increasing, right? So now here one thing to remember is polarity of the clock is not essential. That means you can here I have used positive edge triggered flip-flops. So you will find there is no bubbles placed here, right? So in every positive edge of the clock, this will start counting from 0 1 2. So it will sense. If I use a negative edge flip-flops also, it won't make any difference. Only thing is the transition, the count will increase during a negative edge of the clock. So that is the only difference it is going to make. Okay, why I am stressing this point is when we learn about asynchronous counter, the polarity of the clock also changes the direction of the counting. Here that doesn't happen. Okay, it will if it is counting up, it is known as up counter. It will continue to count up. If you are using instead of a positive edge triggered, if I use a negative edge trigger, still it will count up. Only thing is the change which would happen will be during the negative edge. Okay, so that is the only difference it is going to make if I change the positive edge triggers with negative edge triggered flip-flops. Okay, so now suppose I have to make an up-down binary counter, right? Okay, this was an up counter. So if I have to make I have a control signal where I need to count up, and if required I have to count it down also, right? Now if I see this table again about a 3-bit counter, it is 1 1. From 1 1 it has to go to 1 0. Right, this is 3, this is 2, this is 1, and this is a 0 out here, right? Now if you see here, this Q1, Okay, it is 1 here, this is 1 here, so it is not making a transition here. This is 0 here, then it is making an transition here. Again this is 1 here, so it is not making a transition here. Again this is 0 here, so from 0 0 it will again go back to 3, right? So it is making an transition here. So when I have to count down, right, so I will this is 0 1 0 1 0 1 0 1 0, it is continuously toggling, so I can give an T input. Here the difference out here is the change is the toggle or the change in the output state is happening only when the previous lower significant bit is 0, whereas in the first case we saw this is changing from 0 to 1, like here 0 to 1, this is 1. Okay, every time this is making a transition when the previous one is 1, whereas in this case it is making a transition when it is 0, because it is counting down. So that is the only difference out here. So accordingly I can take either Q or Q bar, right? So now suppose I want an up counter, so I give up signal is equal to 1, down signal is equal to 0. So if I give down signal is equal to 0, this AND gate will be disabled, it will be 0. So on the left hand side these two AND gates also will be disabled. On the right hand side these AND gates will be enabled. So up signal is coming here, so I am giving it as a T. Now this Q this is enabled, so this Q is given here. Again this Q, right, and you have an AND which is doing an AND from the previous stage, and you are giving it as a toggle. So it will count up now in this particular configuration. So this circuit will count up. Right, now in case I give up is equal to 0 and down is equal to 1, so up is equal to 0, what happens is you will see here this gate will be enabled now. Down is 1, so up is 0, so I'll get 1 here. So through this, so in the first stage it is not going to make any difference. You are giving T, so it will toggle with every clock, right? Clock is parallelly, clock given to all this is parallelly. Now all these two AND gates from which was being driven by the up signal, they will get disabled, and these two AND gates which is being driven by the down signal, they will get activated. Now what is the input for this? It is coming from Q bar here, right, and here also it is from Q bar, right? This is Q and Q bar. Okay, that is why the bubble is placed here. So now since you are using Q bar signals out here, this will start counting low. So I can use this counter as an up counter or as an down counter. So this is known as up down binary counter. Is it understood? Abhishek, Ayushman, Sachin? Okay, right, now I can even have an synchronous BCD counter, right? So BCD count, what is a BCD counter? It will count from 0 to 9, right? So I require an 4 flip-flops, right? 9 is 1 0 0 0 1, right? So 8 plus 2, so 10, 8 plus 1 9, and then it will come to 0 here. So I require a 4 flip-flops. So it has to start with 0, right, and it has to go up to 9, and then it has to come back to 0 here, right? So this is known as a synchronous BCD counter, right? So now if you see here, if I take an A1, right, it is has to, this is the next state 0 0 0, I have 0 0 1. If it is 1, it is 2, it is, this is the next state. So I can write present state, and I can write next state. Now output is when it reaches the maximum value. So when it reaches the maximum value, the output goes to 1, and in the next clock it has to go to back to 0 here, right? So that is why I have written 9 here and 0 here. So this is now I have to give the inputs to the 4 flip-flops. Okay, now it is just written 1 2 4 and 8 just to, because it's an BCD counter. So otherwise it is an bit 0, B1 B2 B3, you can call it B0 B1 B2. There are only 4 flip-flops, right? Okay, so just don't get confused with 1 2 4 8. Okay, it is the 0 1 2 3 bits only. Okay, so I have an 4-bit counter. This is it, right? Now if you see here, once it reaches 9, it has to go to 0. So how to realize the circuit? So one option is, so I make 4 flip-flops like we learnt about sequential design. How to do? We write the present state, we write the next state, and then we write either, if you have to implement it with D flip-flop, we write what is D, and then try to use a K map and try to find out what is D, or if we use JK, that we saw in the last class, how to design a sequential circuit. So similarly, if I have to use an toggle flip-flop, right, and I will write the T1, T4, T8. It is actually T1, T2, T3, T0, T1, 4 flip-flops. Okay, you just don't, this nomenclature is slightly different out here, that's all. So these are the 4 T inputs for the 4 flip-flops. So now if you see here, this is 0 to 1, it is changing. So I have input which requires to be given here is 1. Here it is again toggling, so it is 1 here. So here everything is toggling with each clock, so that is why all are 1 out here. And similarly here it is toggling only when this is 1. So 0, initially it is not, T is to be 0, then T1. So I can write these truth tables here, right? Now for finding out what will be the circuit, I can write make an K map. This is a 4 variable K map. This is the output. So for each combination I'll have to make 4 K maps. Okay, that I can do that. And after 9, rest of the input combinations I can use it as don't care also. So that will simplify the design. Okay, that we can do that. But here if we visually see it also, we can rather than making K map is an option available. But if you just see the input pattern, right, you can without even making a K map, directly we can find out what should be the value. So here if you see, it is 0 1 0 1 0 1, everything is toggling out here, right? So you can straight away write T1 everywhere here, T1 as 1 here, right? What about T2? If I see T2 here, right, whenever there is an 1 here, right, whenever there is a 1, it is making a transition. Whenever there is a 1, it is making a transition. Whenever there is a 1, it is making a transition. Whenever there is a 1, it is making a transition, right? Okay, coming to here, and whenever there is a 1 here, right, and I have reached 9 here. In the next thing, it has to make an transition out here again. Okay, whenever I am talking about just A2, whenever there is a 1 here, it is making a transition. There is a 1, it is making a transition. There is a 1, it is making a transition. Here there is a 1, right, it is not making a transition because I am going to 0 out here, right? Okay, let me just focus on A1 and A2. Whenever A1 is 1, it is making a transition 0 to 1. Again there is a 1, it is making 1 to 0 transition. Okay, here again there is a 1, it is making 0 to 1 transition. Here there is a 1, it is making 1 to 0 transition. Here there is a 1, but this is from 9, instead of going to 10, I am coming back to 0 here. So it is not making a transition here, right? That means at this particular 1, and I need to mask the transition. Okay, so what can I do? If you see here, this is 1 here. Okay, for all these ones, it is 0 here. So only for this particular 1, it is 1 out here, right? So what I can do is I can write T2 as A8 bar A1, right? Okay, that is this. Okay, A. So when this is 1, I take for these ones I have enabled because I have taken A8 bar, and here I am disabling this particular 1 to for this one should not result in a toggle. So I am putting A bar. So that if I take A8 bar and do an AND with this one will get masked. Okay, because it is becoming 0 here. So that is the reason I do this, right? Okay. So what about next? Now here if you see here 1 1, it is making a 0 here. So I will take an AND of these two, so that there is a toggle happening from here to here. Again 0 0, no toggle, 0 1 no toggle, 1 1 1 1, it is again making a toggle. So simply A4 I can simply write is AND of A1 and A2. So this is A1 and A2, right? Now what about the third one, the final one, right? Now if you see here, this is making it, initially it was 0, it is making a toggle when all the three are 1, right? So one condition is that, and then again it is making a toggle when it is 0 0 1. It is making a toggle out here from 0 0 1 2. So if I use a condition of 0 0 1, right, if I use this particular condition, then that is occurring here also, right? Then it will toggle here also. So I can't use 0 0 1. Instead, if you see here, this 1 and 1 is a unique condition. So I will use A8 and A1, right? And I can use A8 and A1 for toggle, and also this condition. So this condition is unique, right? This is happening only once in this table. So I have an A1, A2, A4, and also this condition is also unique. So I write an A8 and A1. So I write A8 and A1, right? So these for these two conditions, so the T input will be less. So if I realize a circuit, so so I can realize a circuit like this, right? So these are the equations, and so for T1 I can give 1 straight away. For T2, the toggle of the next most significant bit, A8 bar and A1. So for the next signal I will put an AND operation. So this is how I can design. Okay, this I have explained it by seeing a visual inspection. Because it is going sequentially, right? So that is the reason. But if I say for some requirement, I require some random series here instead of 0 1 5 6 7 8 and then come back. So in that case, the only option available with us is to write the present state, next state, and then you have to write an T1, T2, T3, T4, whatever it is, and then use K-map and find a solution for the T signals, right? So that is how you'll have to do it. Okay, but for these, these are the standard circuits. So just by looking at these tables, you can find out solutions directly. Okay, so this is one way, one synchronous, and then we have this is binary counter with a parallel load. Okay, so this is an what does it do is it's an normal counter. So the clock is given to see all the three the same clock because it is synchronous counter, and here you have JK, JK, JK. When the count signal is high, you will find this is going high here, and this is also going high. So J and K 1 1, so it will start counting. So now A0 is given here, right, through this AND gate. It is given here. So this will be J and K also will be 1 here. The other input to the AND gate is coming from the count signal, right? So from the count signal, so this will start counting. The only additional provision which is given here is load. Okay, what does load? Whenever the load signal is high, right, whenever the load signal is high, what happens is this will go 0. So the count signal will get disabled. Okay, the count signal will get disabled, right? And what happens is now if you see here what is going into this OR gate now, if the load signal is 0, these AND gates gets enabled. All these AND gates will get enabled. Okay, now you have D0 coming here. So I have a D0 through this AND gate going to J, and D0 bar going to K. That means if D0 is 0, I will give 0 1 here. So this will get slaved to 0. If D0 is 1, then I'll have 1 coming here and D0 bar coming here. So it will become 1 0 because JK 1 0 will put it to 1 and 0 1 will put it to 0, right? So what happens is that it will start acting like a D flip flop, right? Now if you see here, so whenever the load signal is going high, whatever is the input given here, okay, that gets loaded into the flip-flop, and then the load signal goes there, and then with count signal it will start counting upwards from there. So when you have an say n-bit counter, so you can have this kind of arrangement to initialize the counter with any value you want, right? So you want it to start, say, counting from, instead of 0, if I want it to start from, say, 1, then I'll place 1 out here and give the load signal high for a short duration of period. So in that small pulse, whatever is the value of given in the input, that will be captured into these registers, right? So this will the count will start from there. So that is why we use D0, D1 and D2 and this load signal. Is it understood, Kishan? Have you followed it till here? Yeah. Okay. Now this is like the explanation, same what we have explained. So if now also clear is given here, okay, the clear, there is a bubble out here. That means whenever the clear signal is 0, this entire data will get to 0, right? So that is whenever we want to clear the counter. Okay, so that is there. So if you find here, whenever the clear is 0, irrespective of clock load, all the counters will be set to 0. And now when the clear is 1, only then it will start functioning. Now if I put load signal 1, then whatever during the positive edge of the clock, whatever is the inputs, that will get loaded. That means if I go back here, okay, clear has to be 1, otherwise if clear is 0, all will be 0. The clear is 1 out here, and I have given load signal as high. Load signal is high, this is 0, this is high, so all these AND gates will be enabled. So whatever is the inputs available here, that gets loaded onto these flip-flops, right? So load inputs, and if the load is 0 and count is 1, then it will start counting upwards, right? When load is 0, then all these AND gates will be disabled. This counter is enabled here, so all JK will be 1. If this is enabled, you will find this is 1 here, this is 1 here. So JK 1, JK is 1, so they will all start toggling. So it will become a normal up counter. So it will start counting up, right? So and also if you give load 0, count 0, okay, then it will be 0 here, 0 here. So J will be 0, K will be 0. So whatever is the count, and it will hold that particular value as it is. So that possibility is also there with this implementation, right? Now there are other counters also. So one is known as an ring counter. Okay, there are 2-3 counters which we'll see how these counters work. The one is known as a ring counter. So you have given in the ring counter, initially I load 1 0 0 0, right? So now it is a shift right register, right? So this output of this is given as input to this register, this flip-flop. Output of this flip-flop is given as input to this. So this is a shift right register. We saw shift registers also, right, in the last class. So initially I am going to load a 1 0 0 1. So with each clock, what will happen is initially it will be 1 0 0, then this will become 1, then this will become 1, this will become 1, and then here you are putting this feedback here. So initially it was 0 here, now that 0 will come here. So you will find only 1 is available, so that will keep moving, that 1 will keep moving here. So if I see the waveform, initially I have loaded T0 with 1. In the first this is negative edge triggered flip-flop, and this waveform is shown for negative edge triggered flip-flop. So first negative edge, okay, this 1 will be transferred to the next flip-flop. It will go as 0 out here. In the next clock, this will go high, and the next clock this will go high, and then in the next clock again T0 will go high. Now why is T0 going high? Because you are taking the output from T3 and giving back to T0. So once it has reached 1 out here, then again this one T0 will again get loaded with 1 0. So this is the kind of output waveforms which we get. These kind of waveforms are very much used in advanced VLSI circuits and things, where I require 4 different phase of clock, right? So I mean this is known as 4-phased clocks, right? Okay, this is 1, 2, 3, 4. So I require sometime in some circuits I require 2-phase clocks, then it will be 1 0 1 0 like that. This is an 4-phase clocks, and sometimes I require n-phased clocks also. So that means more than 4 also. So hence those types of phase clocks can be generated by using an ring counter. Okay. So this is ring counter, and now if you see here, here we have used 4 flip-flops to generate an 4-phase clock, right? Okay, so I can also generate an 4-phase clock by using just 2 flip-flops, right? So this is a 2-bit counter. This becomes 2-bit counter. And then I use a decoder. So what does a decoder? We have learnt about a decoder in our earlier class, right? So it is going to count 0 0 first, right? It is just a 2. 0 0 will give me a high at. This is a decoder, right? So a decoder, on one of the signals will be high based on the inputs. For 0 0, T0 will be high, then it becomes 0 1, then a T1 will go high, this will go low, and for a 1 0, a T2 will go high, right? And this will be low, and for 1 1, this is a decoder, so T3 will go high. So now instead of using an 4-bit counter, I can just use a 2-bit counter to generate 4 clocks and one decoder, right? So this is more cost effective, right? It just requires 2 flip-flop and 2 4-line decoder, right? So if I talk about an N phase clocks, okay, in that case here itself in small benefit is in, but if it is a say 16 phase clocks I require, then I will require otherwise here I will require in this case I will require 16 flip-flops, whereas I can generate if I use a decoder and a counter combination like this, I can just use a 4-bit counter which will generate 16 different conditions, and then I can use 4 into 16 decoder. So it saves a lot of flip-flops, because flip-flops take a lot of space. Decoders, they don't take that much of space. So this is an option which we can use to reduce the hardware requirement. Okay, and also other option available is instead of a ring counter, I can use a Johnson counter. So in ring counter we saw when we give 1 0 0 0, okay, if I give 1 0 0 0, it will generate 4 unique states. Like if I go back here, 1 0 0 0 here, it is generating 4 unique states, again 4 unique states, right? So instead of that, I can use a Johnson counter. Okay, here I am giving this T bar, and I am the output. The only difference out here is earlier what we did, from T we gave it to D, right? If you see here, right, from T we have given here. So instead of giving from T, if I give from T bar, Q bar, okay, this is a Q bar. I am taking from Q bar and giving an input out here, right? So instead of Q, I am taking it from Q bar and giving it. Okay, if I do that, if you see initially it is all 0 0 0, and I have taken bar and putting it here, so 1 will get will come here, right? Again it is a 0 here, so another 1 will come here in the next. So this is also, this is moving forward. So I have a 0 here, again I'll have 1 here. Now I have all 1s here. Now this is 1 here, so in the next 0 is going to be fed from the left hand side. Now again 0, again so this is moving forward, this is 1, another 0, again 1 0, again finally when it 0 0 1, again all will become. So I have 8 unique states, right? So just by connecting a T bar, giving a feedback of Q bar instead of Q, instead of 4, I am generating 8 unique states, right? So that is also helpful. So I with lesser hardware. So instead of going for an decoder, obviously decoder will give 16, right? But again decoder hardware is required, right? So this is somewhere in between. With 4 I am getting 8, right? If I use Q, I'll get just 4. If I use a Q bar, I will get 8 different states. And if I am going to use an decoder out here, right? If I use a decoder out here and use a simple counter, then more number of states I can get. So this is somewhere in between the two configurations. So this is our okay. Now so this is we saw this. So this is how this is an like for decoding circuit. Like for the 8 different states, I can make one of these going high, right? Like for example, for 0, right? So I taken from here I taken a Q bar. I am taking it here, and then from here I am here the second and I am taking this Q bar. So I am getting a 0 out here. So for 8, this you can just try to map this here. You will get for 8 different combinations, only one of them will go high at any given time. So this is known as a decoding circuit. Okay. Now the problem, there is a small issue with the Johnson counter. So initially, if I feed 0 0 0 here, obviously as I keep this if you see this it is moving towards the right, and this 0 has become 1 and it has come here. Again it is moving right here, this 0 is becoming 1 and coming here. So this will go in this particular loop and generate 8 states. Say when I am switching on the circuit for some reason, okay, with 4 flip-flops, actually with 4 flip-flops I can have total 16 different states, right? So these states, so for example, if it is 0 0 1 0, which is not there here anywhere, so if it is in this state, now if you see here, this 0 comes here, so it becomes 1 0 0 1, and now this 1 is going to come here, so it will become 0 1 1 0. So this will also get into a loop, which is not what I wanted. I wanted this particular loop. So during switching, if for some reason if it is in if it is not the desired 8, if these flip-flops are in any other state, then they will also form a loop, and they will continue to move in this loop. Okay, so that is the reason. So we have to take care. Okay, so we have to do something about it, right? So so you will find here these are the states. So this will go from 0 to 1, and this is the loop. But there are different other possible combinations also. If the flip-flops get loaded with any of these, then they will form an secondary loop out here. Okay, they will continue to remain in that particular loop. Okay, so to avoid that, one option what we can do is, right, we take don't take these as don't care conditions. We will take these conditions also, and we have to ensure that if it is this condition, it has to come to 0. If it is this condition also, it has to come to 0. If it is in this condition also, it has to come to 0. So you can do that kind of thing. If you do that kind of thing, so by some mistake, if it reaches in one of these states, in the next clock it will come into this particular loop. So you can do that. So you can make an instead of using don't cares, if you try to map those conditions, and if you try to get the output to 0, so accordingly you can do that. So that is one option available. So this somebody had suggested this particular option. Okay, so what it does is, whenever it goes into an unwanted state, so these two additional flip-flops, which has one OR and one gate which has been put here, so that will bring back this circuit into the current loop in this manner, right? Okay, so as long as it is there in this particular loop, it will keep running in this loop. Suppose it for some reason it goes to 1 0 1 0, right? Then in 4 or 5 clocks it will come back into this loop, and then it will start rotating in this loop. Similarly, suppose this is for some reason this is the state. Okay, in 2 clock cycles it will come back into this loop. So this is how it is done. Okay, so we can do that. Okay, the other option is each of them This somebody optimized it. It requires very less hardware. Okay. Otherwise, what we have to do is each of them, if this state is there, you have to make a circuit, which will bring it to 0. This will bring it to 0. So you can do that also. Okay. So that is all about synchronous counter. We will take a 10 minutes break out here, and we will talk about asynchronous counter. Okay, we'll start at 3 o'clock. Thanks a lot.